Next, let's talk here a little bit about distances between lines, points, lines, and planes. Let's do the distance between line L and point P, which is, of course, not on the line. All right. So we've got a line L, and this could be three-dimensional or two-dimensional, I suppose. Of course, we know kind of about two-dimensional, but in 3 dimensions, let's say we've got this point P here, and then line L is somewhere out in space here, so let's just kind of denote L this way. Well, here's what we're going to do. Figure out this distance. If we let Q and R be points on this line, what we're trying to find then is this distance right here, call it D, and we're just randomly picking Q and R, not, let me do Q a little further over here. Shortest distance, yes, shortest distance is what that, of course, refers to. All right, now to get this distance, of course, we know that this is going to have to be perpendicular, isn't it? And you know, it's not necessarily in a plane like in the line's not necessarily in the plane of the board to this. I'm just, you know, it could be out here that my line is, but it's still that perpendicular distance. Here's what we can do. Let's draw this QP vector, and we're going to refer to that as the U vector. And then QR, notice what it is. That can be our V vector, direction vector of our line. Okay. All right. So the first thing we note here is we've got a right triangle, and let's call this angle theta, because how is D and theta and the U vector, how are all those related? Well, isn't the sine of theta equal to D divided by the magnitude of the U vector? Which means that D is the magnitude of the U vector times the sine of theta. Opposite over hypotenuse is what we did there. Okay. Well, that's fine. However, let's notice this. If I think about this angle, alpha, which is the angle between the U and the V vector, those are supplementary. Alpha and theta are supplementary. So what about the sine of theta and the sine of alpha? Aren't those equal? Because alpha is 180 minus theta. So if you think about the sine, this is the way I think of it anyway. Here's theta. 180 minus theta would be here. And so those are going to have the same sign, aren't they? Because they're, you know, the y values if we're using the unit circle and all that. So yeah, alpha and theta are going to have the same sign. Okay? Well, that's fine. But if I multiply this thing by the magnitude of v, which may seem strange, but let's notice what we get out of that. You get the magnitude of u times the magnitude of v times the sine of alpha over the magnitude of v. You notice anything about this? We actually don't have to, it's the magnitude of the cross product. Yeah, it turns out that you can, if you know that angle alpha, but that would you'd have to figure out some angles and things like that. It turns out though, you can just do the magnitude of the cross product of u and v, and that'll give you your distance from that point to the line.
So that's a vector. Oh no, that's a scalar.
Yeah.
Okay.
So this will just be a number. All right. So let's put one here. Example up here. All right. So let's find the distance. And notice here, the v is. We'll have that if we have the parametric form of the line or whatever form of the line. We'll have that v vector because the v vector is just the direction of the line. So you'll have that. You'll just have to, on this one, we'll just have to figure out what the u vector is. Not too bad. So find the distance between the point 3, 5, negative 1 and the line x equals 2 plus 3t, y equals 5t, z equals 4 minus t. Okay. Well, like I said, the v vector, the direction vector, comes right off of that, right? Because the direction vector would just be the a, b, and c here, so it'd be 3, 5, and negative 1. Okay. Then the u, that's kind of arbitrary. We can use any point we want to determine u. You remember u is just, here's your line, here's your point. U is just from any point on the line to the point. So it's just another vector and so we can use any point we want to here, x, y, z, and a good x, y, z point to use would be what? T is 0, 2, 0, 4. And so we can use that and then point that to 3, 5, negative 1. So u, in that case, would be, just subtract the components, right? 3 minus 2, 5 minus 0, negative 1 minus 4. And so that's our u vector. And so the distance then is the cross product magnitude over magnitude of v. Just have to, let's line it up like this. I like to do it. You can do the determinant thing for that, but if you line these up like this, I think it's fairly easy to get the cross product. Remember the cross product, the first one is the determinant. The first component is the determinant of that, 2 by 2, so it'd be minus 5 plus 25. What did I say? Minus 5 plus 25. So that's 20. Then cover that up. It's minus that, though. The determinant there, so it's negative 1 plus 15. So that'd be 14. So it'd be minus 14. And then determinant there, so that's 5 minus 15. That's negative 10. So we need the magnitude of that. Does that sound okay? All right, minus 10, there's positive 10. Positive 10 on my paper. I think it's negative 10. Won't matter when we do the magnitude anyway. All right, what about this? How do we do the magnitude of a vector? Just do the square root of all the squares, sum of the squares. So the magnitude of V would be 9 plus 25 plus 1. So this would be the square root of 400 plus that squared would be 196. That squared would be 100, so that would be the magnitude of that. And that's 35. So it's 696 divided by the square root of 35. And that might simplify a little bit, but square root of 696, that almost seems like it. That's not a perfect square, is it? Oh, okay. They'll usually just, if it doesn't square root nicely, they'll just do it something like that.
Yeah, I did the square root of
Okay. About 4 units. Okay. All right. Now, similarly, we can find the distance between a point and a plane. The formula just slightly changes. Let's go through that. Okay, so we start off with a plane here. And a point somewhere not on the plane. That's our XYZ. P. Point P. All right, so of course we're talking about the shortest distance. And so again, that's going to drop down vertically to, or come to vertically. It may not be straight down like I've got it, but anyway, yeah, that's going to be perpendicular to my plane there. Okay. All right. Now, to set up our triangle here, let's notice that yeah, we can also get a right triangle going on this one. Let's do it this way. So that's 90. So we've got a nice little triangle here. We do another point on the plane, X, call it X0, Y0, Z0. So that's any point on the plane. Well, let's also do what we did with the line there, and let's make our U vector from that point on the plane. Call it the U vector. And so the distance, if we call that, let's call this angle here theta. Our distance then, which is right here, our distance would be, well, cosine of theta would be d over the magnitude of u. And so the distance would be the magnitude of u times the cosine of theta in this case. Well, obviously we know here d is going to be parallel to the normal vector. Yeah. Yeah. And so if I multiply here by the normal vector magnitude, normal vector magnitude, I get the normal vector magnitude times the u vector times the cosine of theta divided by the magnitude of the normal vector. That's our dot product. I think they do. It's a little different, maybe. So now, the dot product is a scalar. And sometimes the dot product can be negative. And so for that reason, we're going to ensure that the dot product is positive, we're going to do an absolute value of it, divided by the magnitude of it. And so that's going to give us the distance from a point and the plane. Okay? So let's see. Find the distance between 1, 1, 3 and then the plane 3x plus 2y plus 6z equals 6. Let's see if we can find that distance. All right, so what is our normal vector here? Well, again, you just read the a, b, and c off of the plane. So it'd be 3, 2, 6. Be the normal vector. All right, then the other thing we need is just a random kind of point in the plane, but if we're smart about this, what could we get here? Do you see any nice little point we could get that would be in that plane? Well, if I let x and y be 0, I've got the z as what? 1. Okay, so yeah, just look for nice little, I mean, we could do the same thing for y and z being 0. Yeah, you could do either of the two zeros, and usually that turns out pretty good. But anyway, that's the one I saw when I was doing this. Okay. All right, which makes u then is from the point on the plane to the point we're trying to find the distance to. And so we're just going to do u, the vector from this to here. So yeah, just subtract. So it'd be 1 minus 0, 1 minus 0 again, 3 minus 1 would be 2. So that's our u vector for our distance. So the distance then is the absolute value of the dot product of u and n vectors divided by the magnitude of n. So what's our dot product of u and n? 3, just multiply, right? 3 times 1 is 3, 2 times 1 is 2, so add 2, and then 6 times 2 is 12, which are positive, so the absolute value is not going to do anything. What about the magnitude of n? Well, you square them, 9 plus 4 plus 36. Oh, that works out nicely, doesn't it? So that'd be 17 over square root of 49. That's 17 over 7. So that distance, 17 over 7.